In this third example, we've got a number 2 spruce pine fir, which means that we have wood. It's a 2x4 dimensional lumber, which means that it's not actually 2 inches by 4. That's a nominal dimension that then is dressed down. And typically for our engineering calculations, we say 1.5 by 3.5. Right? Its length is 96 inches. There's a second moments of area. They're different, and this is the first time we've encountered this. We've got different ones for this rectangular cross section. Right? So now we come down to back to pretend this is our 2x4. It's not, of course, got the same proportionality there, but one side is much longer than the other side. And when I squeeze it and it goes into the buckle shape, it always deflects in one particular direction. The reason why is everything about the different directions are the same except for that second moment of area. So it's going to buckle about the one that has the smallest of the two, right? We're loading it up from 0, so it's going to buckle the first time it can, and that's going to be the smallest value, which is going to be with relationship to the y-axis, right? So if we draw these in here, the way I've got the 2x4 shown on the page, it's tall vertical. And so that would be your y-axis. There's your x-axis. And so let's, of course, again, look at this. Here's your member, and I start loading it up, loading it up, loading it up, boom, right? So it's, notice how it's bending there, right? That's bending about this y-axis. Cross-section rotates about the y-axis. Right? And so the lowest one that we've got is going to be associated with IY in this particular instance. So pi squared times a much smaller modulus of elasticity than we had before. We were dealing with steel before, and wood is about 1/30th of the stiffness, 1/10 to 1/30th, times our IY value, 1.05 inches to the fourth, right? If you put in the IX, you'll just get a much larger number, about 5 times as large a number. It's going to buckle about the one that has the lowest. And our length is 96 inches. Again, keep track of all those units. Those length units need to all be the same. So pi squared times 1,000 times 1.05 divided by 96 squared. So we have a 2x4 that's 8 feet long, and notice its buckling load is much, 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 much lower than what we were seeing before. It's only about 1.1 kips, or about 1,100 pounds. Absolutely, only 96 inches, that's 8 foot long. And that sensitivity to that length is crucial. You will see this quite often when people raise roofs in houses, that you'll see that they'll temporarily brace some of the roof trusses with a long, skinny 2x4. And you'll see that it's already bowed, right? And that thing might be on the order of 14 or 15 feet long sometimes. And maybe they cobbled something together, but let's just see what that would be. 14 times 12, that'd be 14 feet long. So 168 inches. So pi squared times 1,000 times 1.05 divided by that new length squared, and all of a sudden we're down to only 367 pounds. And they make these things even longer than that, and it's very imperfection sensitive. Sometimes they already come there's almost never a perfectly straight 2x4 to begin with. All kinds of things are happening here that it doesn't take much to buckle these 2x4s at all, especially compared to the equivalent member in steel.